Hello, everyone. I'm Viacheslav Borovitskiy. I'm going to give this mini course on Gaussian random fields in machine learning. So I was going to do this mini course in English, and if there is no problem, I still intend to do so. So let's start. And before we start, I want to say that if you have some questions or comments, please be welcome to interrupt me anytime and ask them straight away. Do you hear me okay? Can somebody tell something?
А можно чуть-чуть погромче?
Do you hear me now? It's better?
Намного лучше, спасибо.
Okay. Yeah, so let's start. The topic for today's talk and for talks tomorrow and the day after tomorrow is Gaussian random fields in machine learning. What is this? Well, this is some part of computer science, first of all, and this is some part that really does help in practice. So that may be interesting from some perspective. And the very exciting thing to me about these Gaussian processes in machine learning and machine learning itself actually is that it's a part of computer science that is rich with interesting analytic and probabilistic machinery. So sometimes computer science is associated to, I don't know, combinatorial methods, algebraic methods, elementary math, and so here it's really mathematical and functional analysis and probability and statistics. So a couple of words about me. Here I am. I'm a final year PhD student at St. Petersburg Department of Stiklov Mathematical Institute, where I specialize at harmonic analysis. And actually this is, my activities there are unrelated to Gaussian random fields or Gaussian processes or anything Gaussian. So also I'm a researcher at Mathematics and Computer Science Department of St. Petersburg University and at Euler International Mathematical Institute. I'm one of the people in our department involved in industrial collaboration with companies such as Gazprom Neft and Huawei. And actually this is the place where I first met Gaussian random fields when I was doing a project on applying these Gaussian random fields in geostatistics in a group led by Professor Lifshitz, working on a project for Gazprom Neft. And since the end of 2019, I was doing some Gaussian random field related machine learning research. It was done in collaboration with the statistical machine learning group of University College London. And we managed over the last couple of years to publish several papers at top machine learning conference like ICML or NeurIPS. And one of these papers even got this great award. And basically this is the story how I came to do these Gaussian processes and why I'm here to give you this talk. In this mini course, there will be 3 lectures. And the first one, which is today, I will give some introduction to Bayesian methods and Gaussian process regression, the main algorithm based on Gaussian processes in machine learning. And I will talk a great deal about applications of these methods in real-life problems. Today, there will be almost no formulas and somewhat hand-wavy exposition with lots of pictures. So it's planned like an overview, relaxing talk for today. For the next 2 days, I will dig into something more rigorous. So tomorrow we will address the algorithms for predicting with Gaussian random fields and generating their sample path. During the course of this lecture, I will give a more rigorous introduction to Gaussian process regression that we will see today. And I will discuss the basic algorithms in a rigorous manner on how to sample and predict with them. We will finish by asking this question on whether or not we can do better, whether or not we can create some more efficient algorithms. And in the third lecture, I will talk finally about the efficient algorithms for sampling and conditioning. First, we will discuss sampling from stationary Gaussian fields, then sampling from conditional Gaussian fields, approximate conditioning of Gaussian fields, and of course, as it's the last lecture, there will be conclusion. So that's the start of today's talk. Introduction to Bayesian methods, Gaussian process regression, and applications. The outline of today's talk will be like this. So first, there will be some additional introduction, just a couple more slides. Then I will talk about Bayesian inference for an unfair coin. It's probably the simplest example of Bayesian inference, and I'm going to present it just for the reason of presenting the simplest scenario where these methods work. And then we will talk about Gaussian processes and this Gaussian process regression algorithm, and we will think about this in the light of this Bayesian inference. So, and the last part, applications, probably will be the largest one. I will tell you how these Gaussian random fields are applied in different areas, such as geostatistics or optimization or robotics and control. So let's start for today. And first thing that I want to say in the introduction is this note about language. First, I will consider the terms Gaussian processes and Gaussian random fields interchangeable and synonymous. There are maybe some subtle differences between them, and we will briefly discuss this in the next lecture tomorrow. But all in all, in the machine learning, at least, they are used interchangeably, and actually Gaussian processes is the preferred term. Next thing is this Bayesian language. So sometimes I may use the Bayesian language. It's some notation and naming conventions that are used by Bayesian statisticians and that are very widely spread in machine learning community. And basically, the main example of this language is as at the bottom of this slide. So we have two functions which are denoted by the same letter P, but actually there are two different functions, and they different because their argument is named differently. So P of A is density of random vector A, and P of B is the density of random vector B. It's not function P evaluated at A or B, it's different functions, and they're evaluated at different points. I will try to stick to more conventional and less confusing language, but sometimes I might need to use this Bayesian kind of notation. Yeah, so Gaussian random fields or Gaussian processes are indeed useful. I want to prove you this right away by showing this header of the paper. It's called Bayesian optimization in AlphaGo. As you might know, AlphaGo is the software that was used, that managed to beat a human professional Go player. It was several years ago and a big success for machine learning. It was made by this DeepMind laboratory in London, and it consisted of many different tools, models, components, and so on. So this was a complex system. And one of these components was this Bayesian optimization that was used to pick the best parameters for running the software, for running the training for this software, and for doing this the problems of this kind. And Bayesian optimization is the Gaussian process based algorithm, which we will discuss in the end of this talk in the application section. So they used Gaussian processes to help in designing this AlphaGo software that beat humans at the game of Go. Yeah, so let's now study Bayesian inference for an unfair coin. The problem setup is as follows. We want to estimate the unknown parameter of an unfair coin. So usually coin is 50% times heads and 50% times tails. But an unfair coin may be, for example, 75% times heads and 25% times tails. So we imagine that we don't know how unfair a coin is, and we want to deduce this from the observations of how the outcomes of this coin toss are generated. So more formally, we can say that we have some random variable x, which models this unfair coin. And it has the usual Bernoulli distribution. That is, it takes two values, 1 for heads and 0 for tails. The probability of 1 is p, the probability of 0 is 1 minus p. And we want to estimate this parameter p, which is unknown to us, from some sample of this random variable x. There are two approaches to how we can do this. And this division is, maybe it's even like in a philosophical plane. So the first one is this frequentist approach, which is usually taught in the statistics courses at universities. And with this, the answer will be some number, p hat. So the parameter, which is most probably, so to speak, characterizes the unfairness of this coin. The tool which will be most likely used is the maximum likelihood estimation. And it will look something like this. This p hat parameter is the parameter that maximizes this function. And this function is actually just p in the power of the number of ones that we get times 1 minus p in the power of number of zeros that we get. So the usual likelihood function, which we optimize. There is also this Bayesian approach, which will be very important for the course of this talk. And here the result is quite different. The result of estimating parameter P is actually not a parameter, but a density, a probability density function, rho hat of P. It is inferred using Bayesian theorem. And also to do this inference, we require some prior density over this unknown parameter P. So the process is like follows. You take this parameter P and then you summarize your prior conception about this parameter into the prior distribution. Then you have this likelihood, which is like here, and which is given by this assumption of Bernoulli distribution of this variable. And then you can use Bayes' theorem to get the posterior distribution over your unknown parameter P. And it's why is it better than the maximum likelihood estimation? Well, this is because there is some uncertainty associated to the estimation. So a maximum likelihood estimation just yields some number and doesn't tell you how certain we can be that the number is actually as we given. But this Bayesian approach also characterizes uncertainty in the form of this posterior density P hat. So this posterior density will be proportional to the same likelihood function that we had before times the prior density function that we defined somehow here. It's proportional because the function on the right hand side is not a normalized density, so its integral is not necessarily 1, and we need to divide it by some constant to make it integrate to 1. So it's maybe it's best to see on the picture how this looks like. As I've said on the previous slide, we have this, we have to pick some prior distribution, rho of P. And here I will assume that we have no prior conception about what parameter P should be like. And because of this, the prior is just the uniform distribution over the interval 0, 1. Over the interval 0, 1, simply because it's a probability parameter and it should be contained in this interval. And then we have this Bernoulli likelihood, which comes from the assumption that our random variable is the Bernoulli random variable. So probability of x being equal to some v, given the fixed parameter p, is as follows. So let us assume that the true value of p is 1/2. It's here on the plot with the purple vertical line. So actually the coin is fair. And here with this orange line, we have the prior distribution. And then on the next step, this will be the posterior distribution after some observations come. So let us observe something. For example, we can toss a coin and 1 is our sample. So then the posterior density will look like this. We just used this formula from the end of the previous slide, and it's this line. It's maximal in the point 1, because we just observed 1, but still, for example, if you take the expectation of this, density, it will not be 1. So then consider what maximum likelihood estimation gives you here. Well, it's exactly 1. So after tossing one coin, after tossing a coin once, the maximum likelihood estimation has given us some answer, but it's completely certain in that it's 1, while we know that it's actually 1/2. So that's kind of an advantage of this Bayesian approach, because here we have retained large uncertainty, while maximum likelihood estimation just returned some wrong answer. So we can do this several more times. And we see how this density changes, and it's never like a straight vertical line. So some uncertainty is also always present, but it's reduced. So if we compute variance, for example, it will be smaller at each step. And the maximum likelihood estimation starts finally to go into the right direction of being 0.5. So more steps and even more steps. The answer of Bayesian approach is this density, bell-shaped curve, while the answer of maximum likelihood estimation is 0.5. So at this point, both approaches are more or less converged. So to summarize this, we have Bayesian inference as this kind of machine which takes some prior, which summarizes our prior beliefs about an unknown variable. We have likelihood, which says us how probable is some data given some value of this unknown parameter. And then combining this with data through Bayes theorem, we get posterior distribution over unknown parameter. Not a single value of unknown parameter, but a distribution of this parameter. So most importantly, Bayesian approach quantifies uncertainty. Yeah, and so here I want to, like prior to the further discussion, I want to mention that Gaussian processes are just some non-parametric priors over functions which are used in this kind of inference. So our unknown parameter is a function. We place a Gaussian process prior over this parameter, then we use Bayes theorem, and we get some posterior distribution, which will again be some stochastic process. And it's non-parametric prior over functions in the sense that you may, for example, consider a distribution over functions of form of linear form, where you place some distribution over their coefficients, and then it will be kind of a finite dimensional distribution. And in the Gaussian process case, you get this kind of infinite dimensionability or infinite complexity right away. Maybe there are some questions. Okay. Let me proceed to this algorithm called the Gaussian process regression. As I said on the previous slide, we can consider Gaussian processes as distribution over functions. Take this for some time as a definition. It's some distribution over functions. Then we can do Bayesian inference for these Gaussian processes in this kind of pipeline. First, take some hand-picked Gaussian process as a prior, take noisy evaluations of the functions of the unknown function as data, and define likelihood through Gaussian noise assumption. While it may be not completely clear right now what this means, we will rigorously define this in the next lecture. For now, just assume that this means that noisy evaluations means Gaussian noise evaluations. And so with this setting, the great thing is that the posterior distribution over functions will be not just any stochastic process, but another Gaussian process. So it remains in the same class of stochastic processes. This will be very important because Gaussian processes are, in a sense, the simplest of the stochastic processes. And it's very important to stay in this class to be able to algorithmically model something. Let us explore this pipeline visually. So in these slides, there are samples from the prior Gaussian process. So as it is a distribution over functions, as we defined it, its samples are actual functions. And on this slide, with every different color, is a different sample of a Gaussian process. We can take much more of these samples here. And now assume that we have this data. And we want our posterior process to respect this data. So what we can do, at least intuitively, is to take only those samples that pass near these data points. Something like this. And actually, this will be sample path of the posterior Gaussian process. Another way of visualizing this posterior Gaussian process is through these kind of pictures, where we draw a mean with this bold blue line. It's also called the prediction, the most likely value which will be taken in this point. And then this shaded orange region is the confidence interval at every specific point. So if we take this point, the height of this region at this point is exactly proportional to the variance of a Gaussian variable that sits here. So it's a measure of uncertainty. Near the points with data, we are very, very certain, but far away, we're very uncertain. So let us now give some, let me give some more intuition on what is a Gaussian process. Again, I will define this in the next lecture rigorously, but now just to develop intuition, consider this kind of ladder of extensions. So first we have Gaussian random variables as distributions over real line, characterized by two numeric parameters, mu and sigma squared. Then we have these multivariate Gaussian random variables, which are distributions over d-dimensional, which correspond to distributions over d-dimensional spaces, and are parameterized by vector of means, mu, and the covariance matrix sigma. And then we have Gaussian processes, which can be thought of as Gaussian random vectors of infinite, maybe uncountably infinite size. So it's distribution over functions from some set x to R is denoted by this notation GP of mk, and it's determined by function m, the mean function, and the two-parameter function k, covariance function. Very similar to how random vector is defined, only here this x set was finite, so the mean function was actually a vector and covariance function was actually a matrix. These Gaussian processes are appealing in practice because of their simplicity among other stochastic processes. So, for instance, they're defined by these couple of deterministic functions, so they can be rather efficiently described. So again, to Bayesian inference for Gaussian processes, Bayesian inference for GPs takes in some prior distribution over functions of form GP mk, where we specified mk, something that we came up with some prior reasons. Then we have noise evaluations of unknown function of interest at locations x1 and so on xn. So at some n locations. And this Bayesian inference return the distributions, the distribution over functions of form, again, it's a GP mk, only here it's m hat, k hat, and it's a different mean function and a different covariance function. Given the functions m and k, the functions m hat and k hat can be computed in finite time. So specifically, we have these formulas, which you are not supposed to understand well right now. The important thing is that consider, for example, k hat, it is equal to k minus some vector times some inverse matrix times some vector. This vector and this matrix are constructed from evaluations of function k, and so we can explicitly construct them, for example, in computer memory. And then we need to solve some linear system, multiply some vector by vector, and we get the result. So this is something that can be really done by computer. Yeah, so on the previous slide, we had what I called Bayesian inference for Gaussian processes. And now more like a larger pipeline is what is called the Gaussian process regression algorithm. It includes Bayesian inference for Gaussian processes, but it also includes some additional steps. It answers these questions on how do we turn this data x1, y1, and so on, xn, ym, into a reasonable stochastic model interpolating it. First step is to come up with some parametric families m theta and k theta for prior mean and covariance functions. So not like in Bayesian inference where we had a particular prior mean and prior covariance. Here we have parametric families. Usually the parametric family for mean is very, very simple, like, for example, it's a constant. And the parametric family for k is something rather simple as well. For example, it may be the density of a Gaussian distribution parameterized by the variance and by some multiplicative constant, which is not like in the Gaussian density, but it's needed for the kernels. So never mind. Actually, we just have this number of general purpose parametric families for covariance functions, and we can use them here. So then we use maximum likelihood estimation to pick the optimal set of parameters theta and the optimal likelihood noise value sigma squared from data. So this is the first time we use data to learn something, but it's not the last time, because then we perform Bayesian inference, but now with the already optimized prior and with already optimized likelihood noise. And as a result, we obtain the posterior functions m hat and k hat. And then we can use, for example, the random variable Gaussian of m hat, k hat at some particular point u as a stochastic prognosis at new location u. So we're getting a question. So you obtained some data x1, y1, xn, yn. So I give you the new x, and what will be y in this corresponding to this x, and you return not a particular y, but this random variable, which has mean and some, for example, variance associated to it. And the other thing that we can do is to use samples of this Gaussian process, of this posterior Gaussian process, as an ensemble of possible deterministic models. So as this is a distribution of functions, we can sample functions from them, and they all will respect data, and they all can be used to make predictions in new points. Sometimes sampling is very important, as we will see later in the applications. So again, let's see these pictures one more time. Samples from the prior, more samples, data comes in, then we have these samples from posterior, and here the blue line is this m hat function, and the height of this shaded region is proportional to k hat uu function. Yeah, so this is a kind of an introduction of this Bayesian view on Gaussian processes. So the main idea is that we use Gaussian process as a prior over functions, and then do Bayesian inference. We can use maximum likelihood estimation to get the best prior among some class of Gaussian processes. And then we can use posterior in a number of ways. For example, we can return random variables as predictions, or we can return samples as deterministic models, which all feed data, but there are like many of them. There is a whole ensemble of them. So the first application, which I want to tell you about, is geostatistical modeling of petroleum reservoirs. Here, the problem is as follows. We have this petroleum reservoir underneath the surface of the Earth, and it's deep below, so we cannot actually see what's happening inside. We cannot see what kind of soil is inside, and so on. But what people do is that they drill wells with two functions. First, to get some oil extracted from this reservoir, and the second, to get some notion of on what's happening there. But these wells are very expensive, so there is a small number of them. And in this picture, we have this space between two surfaces. This is a petroleum reservoir, and these different colored lines are the wells that was drilled into this reservoir. And so what petroleum people do is model they extrapolate the data from these wells to the whole volume of this reservoir with Gaussian processes. So they consider the data along wells as data for Gaussian process, and then they sample the posterior Gaussian process to get possible realization of what may be between different wells. So that's how this sample may look like. And these different colors are, for example, the concentration of petroleum, I don't know, something like this. Actually, it's more complicated, but there is some variable which they are interested in modeling, and they just use Gaussian processes and sample this. The very important thing why they sample here and not just predict is that this variable is usually then plugged in to the, for example, partial differential equation solver, and used subsequently to make some prognosis on how much petroleum can we extract in next month. So the Gaussian process here actually serves as, for example, initial condition or some coefficient of stochastic partial differential equation, which they have to solve. And they solve it by sampling the initial condition or the coefficient, then solving numerically the deterministic partial differential equation, and then estimating the distribution of the variable of interest, for example, number of petroleum that they could collect during the next month. So this is an example where we need these samples. As we will see in the next lecture, samples may differ considerably from the mean function, for example, so we cannot just return mean function. It will not be have some physical behavior, but the samples will. So this is the first application. The second application is Bayesian optimization of expensive black box functions. This is exactly the algorithm that was used by the creators of AlphaGo, and here are its insights. So the problem is to minimize some target function phi from Rd to R, and assume that at nth step we has already evaluated it at points x1 and so on xn. So the question is, how do we choose xn plus 1? This is the very usual optimization setting. So nothing Bayesian or Gaussian processy here yet. But now we answer this question by using Gaussian processes. We use Gaussian process regression on this data x1 and so on xn, phi of x1 and so on phi at xn. So we build stochastic model that fits this data that we already have observed. And then we use this model to guide our actions at choosing the next point of evaluation. So for instance, we may choose this xn plus 1 as the point that maximizes the probability that f of x will be lower than the current minima. So, and we can compute this probability because f of x is not phi, it's not unknown function, rather it is our Gaussian process model which we built here. It's also called the surrogate model. So we change the actual function phi for this surrogate f, which is a Gaussian process, and we use it to guide our decisions as if f wasn't actually a phi. The great thing is that this probability is very easy to evaluate. It's just some cumulative density function of normal distribution. And again, so we changed the optimization problem that we had into another optimization problem, but this optimization problem is usually much simpler. So this is why the algorithm has expensive black box functions in its name. It's only good for the functions which are very expensive to evaluate. For example, if you need to pick some training parameters of machine learning algorithm that will run for several days on a cluster of several, I don't know, supercomputers, and this will give you only one value, phi of x1, for example, the precision, the accuracy that we get on the test set. Compared to this, to the complexity of evaluation, this function phi, this problem of this optimization problem, which we use on every step, is very, very simple, and so there is no problem in solving it. It's usually solved by the simple gradient descent with multiple starting points. We actually can pick another decision rule, and we actually can pick any decision rule that we think is best here, but I will show just one other example. We can pick x that maximizes the expected improvement over the current minima. The important thing here is this maximum between the improvement and 0, because if there was not this maximum, then we will not, this function wouldn't depend on variance, but only on the mean function of Gaussian process. And we want to take uncertainty into account, so that's why this maximum here. And also, so this expected improvement decision rule and the maximum probability of improvement decision rule, they are both widely used in practice. Also, these decision rules in the context of Bayesian optimization are actually called acquisition functions, just a synonym of decision rule in this setting. The great thing is that this kind of algorithm does automatic exploration-exploitation trade-off. So the algorithm are faced with the problem of choosing where to evaluate next point, and it may either choose the point where we have little knowledge about what's happening in this region of the space which we're exploring, and so maybe some there the function is much less than everything that we've seen before. We can choose then this point, but also we may choose points from the region where we have explored a lot before, and where we have much evidence about that this next evaluation will probably be slightly better than we had before. So in switching between these two regimes of exploration, where we go into regions we don't know anything about, and exploitation where we go into regions we know well, and we want just to kind of rather small improvement of our objective. This is important problem, and this is a great thing it's done automatically by the algorithm, and it's actually induced by this decision rule that we choose to use here. So I have an example here of how this Bayesian optimization works. Let us minimize this Forster function. Just a simple sine multiplied by a polynomial. And so let us choose some prior Gaussian process. I don't want to talk about which mean function or which covariance function I have picked here, but just something very simple. So how does this Bayesian optimization work? At first, we have at random evaluated some point, and here it is. And we built a posterior Gaussian process from this point alone. This Gaussian process has a very low uncertainty around this point and a very high uncertainty here and here. What's drawn with this red curve is the value of acquisition function, or this decision rule, which we should maximize to get the location of the next point we will try. So here it's maximized here, furthest away from the data point that we had, and we decide to, so the algorithm decides to go for exploration and evaluates here. So next, the model has changed, and the acquisition function now looks like this, and it thinks that it was trying here because we may get some improvement over our current minima. Something like this. So this is an interesting step where we have this big bubble of uncertainty, and of course the algorithm decides to kind of destroy this bubble by evaluating in the middle of it, and then there are the other two bubbles. So that's where we are after 20 iterations. And if we compare our model with the target function, we see that it's actually very close to it. And the minima that we found is very close to the minima. So apart from finding, actually, apart from minimizing the function, we actually found also the function itself to a certain extent. Of course, this can be used in multiple dimensions, and that's where it's actually it's used in practice. So, and the last application that I have here is in robotics and control. Some introductory words that the classical control problem is in the setting where physics is known and we want to find optimal control, while the more kind of modern reinforcement learning problem is that do the same while the physics is unknown and you want to learn this physics while you're seeking the optimal control. So at the same time, you have to understand what world do you live in, and to decide how to optimally interact with this world. The second approach is important because it's supposed to bring us the cheap robots for which we most often don't indeed know the physics that they have. It deviates too much from the ideal physics. So you have some cheap manufacturing, and there is many deviations from the design. So you cannot rely on the textbook physics. You have to learn your physics for every particular robot manufactured, if it's manufactured in some cheap manner. Second is that we cannot learn this physics by hand for every manufactured robot because, well, it increases its price. And if we want cheap robots, we will have to solve this problem of learning physics on the way. Yeah, so this is a very important and inspiring problem and setting. And as it turns out, Gaussian processes here help here as well. So I will present this simple approach, which is called PILCO, probabilistic inference for learning control. This is an approach that uses Gaussian processes to model the unknown physics and then to guide decisions. Let's consider the model that can be described by this equation. So it's a dynamical system where each next state is the function of the current state and the control plus some noise. Xt is then the trajectory, ut is control, f is physics, which should be modeled because we don't know it, and we assume that the noise is normally distributed. So what may happen if we try to model this f with some simple deterministic model, and we have a rather small data, so we didn't run our robot for many trials. Then we could have interpolated this data represented by plus signs with this, for example, red curve. And at this new location, we could have predicted the value of 7, for example, the value of -1, for example. But then we could have started with another model that interpolates these plus signs just as well and predict completely different things at this location, at this same location. So there is, when the data is rather small, there exists a number of plausible models, and we don't know which one to use. So instead, what this approach proposes is to use stochastic model and particularly a Gaussian process to feed this small amount of data in a stochastic manner. So now our feed looks something like this. And when we are asked about a prediction at this location, well, first we return this density function. So normal variable with some mean and some variance. But actually, what we can see here is that what we return is that we don't know anything about what is happening at this point. So our data is too far, and we just honestly can say that we don't know what will happen if we try this 7, for instance. And the great thing is that we can use this knowledge of uncertainty to calibrate somehow our decision rule. So it will take this into account and will kind of choose the next action which is best, both from the point of what we can most probably predict and how certain are we in this prediction. So I have this kind of demonstration. This PILCOM model was used to learn a pendulum on a cart to take vertical position with this weight on top. So at the start, it doesn't know any physics, and it can only go to the left and to the right with the certain acceleration, and it observes the value of how far this weight is from the position where it should be. So, and after several learning trials, after a very small amount of learning trials, what happens is that it learns to do something like this. So, yeah. So actually, that's all that I wanted to show you today. As I said in the beginning, this was a very like overview kind of talk. And in the next 2 talks tomorrow and the day after tomorrow, we will dig into some rigorous objects and algorithms used in to make these applications possible. So thank you very much for your attention, and I will be very glad to hear questions if you have some.
I have a question. So the last slide, okay, the previous after that, before pendulum, yes. Why we have this red line like crooked or not straight? This red line, because previous examples we have it straight and there is a crooked version of it.
You mean this one?
Yes.
So it's the visualization of probability density function of the normal distribution that we have in this point. So recall that we, with Gaussian process modeling, we can return a Gaussian random variable. So here at location 7, we return some Gaussian random variable, and its mean is visualized by this black point on this line. Its variance is visualized by the height of this shaded region. And here the additional visualization is that we have explicitly drawn the probability density function of this random variable.
Thank you. I got it.
Okay. Any more questions?
Could you please tell which mean and variance functions used in the previous example where you minimized the one-dimensional map?
So the mean is probably 0, or it's a constant that is used with parametric maximum likelihood estimation. And the covariance function is probably RBF covariance function, or the Matern one, if you know what this means. So I don't know, maybe I can write the formulas. If you wait for 1 minute, I will bring my tablet and I can write you the formulas. Yeah, so here it was. I can annotate. Can you see what I'm writing here?
Yes.
Yes.
Okay. Right. So covariance function would look something like this. Sigma L equals to sigma squared. Sigma squared x minus y squared 2L squared. So something like this, and it's a function of x and y. And these sigma and L parameters optimized through, oh yeah. Does this answer your question?
Yeah, thank you.
Any more questions? Maybe comments?
I have a question concerning the presentation you have shown. Will it be able to share this presentation to revise, for example, tomorrow before the next lecture? Because we can forget some moments tomorrow.
So tomorrow I will kind of start from the beginning and we'll be defining everything in a more rigorous manner. So I don't think that you would need anything particular from this presentation. But I don't know if you need this presentation. I think these presentations are shared through Telegram chat.
Okay, thank you.
There is a question in the chat. In the last Pilko example, what the family of physics functions was used. So the deal is that we didn't use a family of functions. We used a Gaussian process to model this physics, and it is parameterized by the mean function and covariance function, and which mean function and covariance function was used in the particular Pilko example. I don't know. This could be looked up in the paper, but I honestly don't know. some more questions and comments? So, okay, I guess we can finish.